Hi, welcome to another episode of Ordinary Differential Equations. Today we are going to talk about modeling with first order equations. We have a long list of topics to cover, and so let's get started. So you remember that the first order equation for us a of t times y prime plus b of t times y is equal to c of t. For time being, we are just going to concentrate on linear first order equation and then perhaps bring in nonlinear cases in a future lecture. There are many topics that can be covered by this equation. Is one of the amazing aspects of ordinary differential equation that many things that we study in the sciences can be modeled with these type of equations. We said in the very first lecture that's one of the main attractions and selling point of differential equations. The reason they are so pervasive is that many natural laws, they relate rate of change of something to the present value of that. That's exactly what the differential equation is, a relationship between rate and the current value. So for this sequence of lectures, we are going to look at several topics. One of them is called the mixing problem, something similar to what happens in, say, a washing machine. Next topic to look at is the drag force from mechanics. It can be stated as a problem related to, say, a droplet of rain falling or a person with a parachute coming down. Another set of problems that can be attacked in this style is problems in finance where an interest rate is involved and we are trying to calculate the future value or current value of a certain instrument. Another problem from mechanics relates to escape velocity. It's like what velocity should a projectile have to escape from the gravitational field of Earth. Another set of problems relate to population forecasting. This is going to be important enough for us to have a separate section altogether related to that. And there is still a long list of similar problems. So for today, let's go look at the example of a mixing problem. So I'm going to state an example here and then we are going to try to solve it together. So let's see if we can fit all of it here. So the setup is a tank. In this tank there's 200 gallons of water already, and inside of this there is 50 pounds of salt dissolved in that liquid. So that is the initial condition of our problem. Then we are going to have two pipes. One pipe that's going to let a certain kind of a solution to come in, and another pipe that is going to take the solution out. The incoming solution itself is coming at the rate of 5 gallons per minute, and it has half a pound of salt dissolved per gallon of that incoming solution. The outgoing is going at the rate of 2 gallons per minute. So the problem states just what I mentioned. So what is it that we are after? We are going to be looking for several things. Find the amount of salt in the tank at any given time prior to overflow time. Find the concentration of salt at overflow time. Find the concentration of salt if tank had infinite capacity. And finally, explain how to obtain the answer to this very last part without doing any of this and without having even taken a course in differential equations. So the last question is asking on your just common intuition or in engineering intuition as to how to approach certain problem without getting tangled with all the mathematical detail. So this type of problem is referred to as a mixing problem. It is a very standard first type of question to consider here because all the quantities are very familiar to us. And it's also very amazing that it relates to a differential equation, and the methods that we have solved are going to be helpful in finding the items we are after. So what are the cast of characters here? As usual, problems in this section, everything ties to time because rate of change pretty much all the time is with respect to time. So we are going to have Q as a function of time is the quantity of salt in the tank at time t. V of t is the volume of solution in the tank. Now before we go any further, can you find for me what this functional form is? What is V of t? Remember that we have an initial value 200 gallons and some water is coming in and some water is taken out. So if I wait 10 minutes, how much would be the water level in this tank? That's why the problem is referred to the overflow time. The way it is set up, we are going to have an overflow time. So problem can be three types. It can overflow, it can drain completely, or it can stay at the fixed level. Well, this problem already telling us it's going to overflow. And what we want first is what's the volume of the solution in the tank. So as we mentioned several times, you just come along and try to solve some aspects of a problem all by yourself. So this is a good time to think what is the volume. Okay, so I hope you quickly found out what that is. The volume, of course, is pouring it at the rate of 5, is taken out at the rate of 2. So every minute we have 3 gallons extra in the tank. And at the beginning we had 200 gallons, so 200, so let's write in blue, 200 to begin with. We are pouring in 5, taking out 2, 3 gallons per minute, so I multiply by time, t measured in minutes, so let's indicate that in minutes. So of course my volume is going to be 200 plus 3t, and it's easy to see where the overflow is going to happen. When this becomes 800, that's when it's going to start to overflow. So when I set this thing equal to 800, overflow time itself is going to be at 200 minutes. So overflow is at 200 minutes. Now next question is concentration of salt in the tank. That is separate from quantity. Quantity is the total amount of salt. And what is concentration? Do you remember from your basic science classes? How do you find the concentration? Concentration is a ratio of two things. How do you find it? So concentration is, of course, is the quantity that you have divided by the volume in which it is dissolved. So whatever quantity we might have at a certain time, Q as a function of time. Volume, we just obtained the volume, is 200 plus 3t. That's the volume in this problem. Okay, so this is a description of the cast of characters. Now the question is, where does how does this thing relate to differential equation? That's the amazing part of it, and that's, as we said, is the selling point of differential equation. So we are going to concentrate on what's happening to the main character being Q. This Q is changing. This is the quantity of salt is changing. Why is it changing? Well, because we are pouring some salt in. This liquid that's coming in has some salt in it, and of course we are taking some salt out, so this Q is changing. So we can go back to concepts of calculus. If something is changing, we can calculate the rate of change. Rate of change of Q is dq dt. That's how much the amount of salt is going to change in the tank per minute. Well, why is it changing? We said we have two reasons it's changing. It's coming in and it's going out. Notice that in this simple case, we don't have any chemical reaction, and nothing is producing salt, nothing is consuming salt. So in more advanced problems later on, perhaps you are going to have a situation where some reaction is also happening. But in this simple case, we have no reaction. Either it's coming in or it's taken out. So what we do here is to figure out the rate at which we are pouring the salt in. That's is going to be added, and then the rate at which we are taking it out. If we subtract these two, this has to be equal to the dq dt. Essentially, it's a statement of conservation of the amount of salt. We are doing accounting for the amount of salt. Well, rate in. We have a volumetric rate. 5 gallons is coming in. Each gallon is half a pound of salt. So overall, how many pounds of salt coming in a minute? So we just simply multiply these two. I'll have 5 gallons per minute times half a pound of salt per gallon. That's taking account of incoming. Outgoing, well, it's now 2 gallons per minute going out. And how about this number? For the incoming, I had 1.5 pound of salt per gallon. What should I write here? What is the concentration going out? That's the crucial point of this problem, and I want you to spend a good amount of time reason it for yourself as to what we should put for outgoing concentration. What is that number? Okay, so give yourself a few minutes, as long as it takes for you to reason it out. Now, this concentration is changing. That's what the problem is essentially after. We don't know any number for it, but we know concentration of salt in tank at any time is this ratio. So that's just what I am going to write here. So it's going to be Q. Q means Q of T divided by volume. Volume happens to be 200 plus 3T. The volume is changing as time passes by. So that is our differential equation. Again, the selling point of this course is that we can track the changes by writing a differential equation. So here is my ODE. And then I have a statement of what happens at the beginning of this process. At the beginning, we have a certain amount of salt in the container. In this case, just 50 pounds. So I have 50 pounds. So that is my initial condition. So initial condition, pretty much all the problems in this section, you need to pay attention, close attention to something in the problem giving us a statement about the initial condition, which we are going to abbreviate this to IC. And these two together form something called initial value problem. Initial value problem, abbreviated to IVP in mathematical circles, refers to a differential equation with an initial value. There is another type of differential equation. Sometimes you see that on the cover of your text you are using. It refers to boundary value problems, or BVP. That's a more advanced type of a question. We might come to that in the future. Okay, so we have a differential equation. We are going to clean this up, and then we have to set out to solve it. So without further ado, I'm going to make this thing a little bit shorter. Q prime, that is 5/2, and the other one I might write it as 2 over 200 plus 3t q. And then I have initial condition q0 is equal to 50. So next question. What type of differential equation is this, and how are we going to solve it? What method applies to this? So look at the set of differential equations we have solved before, which category it belongs to, and what method should I use to solve it. Okay, take a couple of minutes. Perhaps rearrange the way this equation has to be solved and start solving it. So this process could, first time around, perhaps going to take you 10 minutes or something, but it is best if you actually solve it by yourself and then come back and compare your solution with what we have here. So due to the presence of this factor t here, this is not going to be separable. We have to approach this thing with the method of integrating factor. If our problem was such that the amount of fluid coming in and going out were equal, this factor will disappear. In that case, you could do it as separable differential equation as well, but here we are pretty much stuck with one method we have talked about, and that is to write this thing. So here's a choice of method. We rearrange it in the style that we had. So I'm not going to rewrite this thing every step, so we are going to bring the initial condition at a later time. So that's our equation. So integrating solve by integrating factor method. So if you hadn't figured this out, again, pause this thing and then try to think how do we get the integrating factor itself. Go ahead through the derivation of the integrating factor. So again, I'm going to insist that you do this thing yourself. What is the integrating factor? Okay. Integrating factor was exponential of the integral of this factor when the leading coefficient is converted to a 1, which in this case it is already 1. So all I have to do is to calculate this simple integral, and then I am almost done. Now it's quite common that students at this stage make a standard mistake of thinking that this is simply to logarithm of that because of the formula they remember that du over u is logarithm of u, or logarithm of absolute value of u. But notice here numerator and denominator are connected to each other, with the numerator being differential of the denominator. There's a little bit of discrepancy here because of this factor of 3. So we have to do a u substitution to get the correct answer, otherwise the problem is going to be lost at this stage. So let's go through that standard procedure. We go take u to be 200 plus 3t. Therefore differential of u is 3 differential of t. I need differential of t in this problem, which is going to be 1/3 of du. So the integral itself was 2 over 200 plus 3t dt. And now with the substitution, this becomes 2. Denominator is u, but instead of dt, I have to write du third. And this becomes 2/3 of logarithm of u. Of course, I'm supposed to write logarithm of absolute value of u, but in this case, u refers to the volume. It's a positive quantity, so not making things even more crowded than it is. There's no need for absolute value here. And in all the integrating factor problem, there is no advantage in dragging that constant with us. We just need one integrating factor. We don't need to have all of them. Okay, so that's a justification why I don't write the plus c, but you could. Now remember, by the rules of logarithm, this can be written as logarithm of u to power of 2/3. That's going to be a crucial step there that we simplify. Now integrating factor is exponential of that, exponential of this. So it's going to be exponential of logarithm of u to power of 2/3, and exponential of logarithm, you remember that from pre-calculus, is the input, and then we go to back substitution. So now I have my integrating factor after all of this work. So our final upshot of all of this thing was that m turned out to be 200 plus 3t to the power of 2/3. That's an integrating factor. So what do we do with it? You remember, we take this thing again. Let me just pause again. Insist that you go through this process again and make sure you got it right. Then if you didn't, first correct yourself and then proceed in solving this and bring it to the conclusion. So one more breakpoint here is that you use the integrating factor we just found and try to go through the next step. So that's going to be standard procedure we are going to have. Break the problem in step by step. You try to duplicate it. First, you try to do it by yourself. If there was a mistake, you try to duplicate it by looking at the solution, and then move on to the next stage, and so on and so forth. So we are going to continue. So what is it that we do now? We take this m and multiply by the equation that has been standardized. There has to be a 1 up front, so I multiply by m. So I'm going to have q prime times 200 plus 3t to power of 2/3 plus that m times this factor as well, so it's going to be 200 plus 3t to power of 2/3 times 2 over 200 plus 3t, that's that factor, times q. Don't forget to multiply the right hand side as well. Right hand side I had a 5/2 already, and now 200 plus 3t to the power of 2/3. Okay, so go ahead and simplify that and write it as a derivative of the product. Again, pause again. I like to look at that picture myself. Pause again, clean it up, check that it is a derivative of a product, and then try to integrate the equation. So every step of the way, you try to go ahead of me by one step, and if not, then come toe to toe to make sure that you follow what's happening. So next, I clean this up. So q prime times 200 plus 3t, the power of 2/3. I write the factor, smallest factor first, then simplify these two. This is power 2/3. This is power 1. 2/3 minus 1 is going to be minus 1/3. So 200 plus 3t. 2/3 minus 1 is minus 1/3. Q. And right hand side, there isn't much I can do at this moment. Next, we pay attention that this is a complete derivative. Derivative of a product. What is that product? So again, you're going to pause here, answer the question. This is a derivative of what? That's the magic of integrating factor method. This all the zigzag we have done, we have created something that's a derivative of a product. The question you're going to answer is a derivative of what? And in all cases, it's going to be Q times your M. Now, there's always a chance that perhaps we have made a mistake during all of our calculations. So we better go double check that our statement is true. So if I have this product and I want to differentiate by product rule, Q prime times the second term. Okay, here's my second term, plus the derivative of the second term. So if I want to take a derivative of this thing, several things are going to happen. One, exponent is going to come down from 2/3, come down by one notch, or 2/3 minus 1 becomes minus 1/3. That's good correspondence. That this step looks like correct. Second step, we have to take a derivative of the interior function, which is going to give me 3 times the exponent. So let me remind you, if I have u to power of n, I want to differentiate that. It's n u to power of n minus 1, then u prime. So let's verify that what we are saying here actually holds water. So this is 2/3. I want to differentiate this whole thing to check. So what do I get? Exponent, which is 2/3. The base, 200 plus 3t to power of 1 less than this. So we need a bit more room here. 2/3 minus 1 times the derivative of the base. Derivative of the base is 200 plus 3t prime. That's the power rule. Well, this is 2/3. This is 200 plus 3t to power of minus 1/3. Derivative of that, that's simply 3. 3 and 3 cancel each other, and I get 2 times 200 plus 3t to power of minus 1/3. So all of this was to convince ourselves that when I differentiate the second, I get this factor. So I'm right so far. Then I write the right hand side, 5/2 times 200 plus 3t to power of 2/3. Well, good so far. Now we go ahead, integrate both sides, of course, with respect to dt. So integral of a derivative is going to be our function, q times the 200 plus 3t to power of 2/3. Integral of this, again, I have to apply a substitution to do this thing carefully. So I write this thing as 5/2. The substitution that we had, that's applicable here as well. You don't need a second one. Maybe I write it again so that we see it at the same time. So again, I'll have u as 200 plus 3t. du was 3 dt, and therefore dt is 1/3 of du. So this is 5/2 of u to power of 2/3. Let me be careful here so we are not making a mistake. This is a dt. Instead of a dt, I need to write du third. So 5, 2, and 3, that's 5, 6. Antiderivative of this thing, so it's going to be u to power of 1 more than that, 5/3, divided by that new exponent, which is 5/3. Now I want to write a constant. Since I use the letter C for something meaningful, concentration, I have to come up with some other letters so things do not get confusing. So I'll say K. That's my constant. So let's clean this up. So I have Q times 200 plus 3t to power of 2/3. Right hand side, 5 and 5 cancel. 6 and 3 gives me a 2. So I'll have 1/2 of u itself was 200 plus 3t to the power of 5/3. And now I have my constant. As soon as the constant shows up, that's a good place to enforce our initial condition. You remember our problem has the initial condition, which is the amount of salt in the tank at time 0, and that is reflected here and again here. So when you have an initial condition, you might as well apply it as soon as the constant shows up. So remember, Q of 0 is 50. So who is 0? Is time is equal to 0. So I go ahead and replace all the quantities. So Q is going to be 50. This is going to be 200 to power of 2/3. Time is 0. It's going to be 1/2 of, now this is again 200 to the power of 5/3. And then I have some constant. So I take this thing to the other side. So I write K is equal to 50 times 200 to power of 2/3 minus 1/2 of 200 to power of 5/3. Now engineering students are very much fond of their calculator. They cramp up their calculator and then get some number here. That's fine. Two issues. That's going to be kind of error prone. Second, is frowned upon in mathematical circles. And third, you might not be able to match that against the solution of your homework system, which might insist on the exact answer. So what to do? One option is just to leave this alone. Second option is to push yourself a little bit further. See if you can actually clean up all the stuff that you learned in Algebra 1 way back when. See if any of that applies here. So of course I have 200 to these powers, and I might think about factoring it. So I factor the one with the smaller exponent, see what happens if I can clean this up. So 200 to power of 2/3 I factor. From the first term I have a 50. From the second one I have a factor of 1/2. Okay, here's the crucial part. What should I write here to reflect what is left after I factor this out of that? Again, this is one of the places that you want to figure that out for yourself to learn what happened. So what is the answer? 200. Well, if this was exponent, say 5, and you were factoring exponent 2, you would have said 5 minus 2. Well, same thing here. It doesn't matter what the exponent is. That exponent minus this exponent, that is the correct answer here. So simply is 200 to power of 2/3. 50 minus 1/2 of, well, 5/3 minus 2/3 is just 1. This becomes 200. And then 50 minus 100 is just minus 50. And I get minus 50 times 200 to power of 2/3. Everybody agrees that this is simpler than that. So when they say simplify the answer, they are after such cleanup procedure. At any rate, we got our K. So try to get your K's exact value, especially if your homework system insists on it, and if it does not specify a certain number of decimal places, that will be your only option. So I go ahead and write my K here. So I have now Q times 200 plus 3t. That's what we are copying now. 2/3 is equal to 1/2 of that same expression to power of 5/3. 1/2 200 plus 3t to power of 5/3, and then I have my constant 50 times 200 to power of 2/3. Now I want my q, so I have to divide by this expression. I notice that this is the same base, so I'm going to subtract the two exponents, exactly what we saw here. So it's 1/2 times 200 plus 3t. 5/3 minus 2/3, that's just 1, so the exponent is just 1. Minus 50, this is 200 to power of 2/3. I have to divide by this coefficient, which is 200 plus 3t to the power of 2/3. So this is q as a function of time. If you want to spell out that this is a function of time, you put the parentheses t in front of your q. So this is what we have found is the answer to part A. Amount of salt in tank well, the problem said amount of salt in tank before the overflow. Of course, after the overflow it's a whole different story, and some other problem has to be solved to figure out what's happening there. But here overflow happens when the volume becomes the capacity. Capacity is 800. Volume is 200 plus 3t. When it reaches 800, it means 3t has reached 600. It means we have hit the time 200-minute mark. So overflow time t is 200. So let's go back, look at the question. Find the amount of salt in the tank at any time prior to overflow. So that means t is less than 200. Then it asks for find the concentration at overflow time. So let's go ahead. So what this thing means is that the answer that we have is good for this span of time, because after the 200 overflow is happening, we have to think about plan B and what happens at that moment. Part B is asking for the concentration. Concentration, remember, it was quantity divided by the volume. So if I take this thing and divide it by, so concentration as a function of time is going to be this divided by the volume, and volume was 200 plus 3t. So if I divide it by that, all that's going to be left is a 1/2. And if I divide by 200 plus 3t again, the exponent instead of 2/3 is going to go up by 1 notch, becomes 5/3. So I let you do a bit of the algebra here. So I divide by 200 plus 3t is 1/2 minus 200 to power of 2/3. And then in the denominator I have 200 plus 3t. Instead of 2/3, it has gone up to power of 3t. So this is concentration up to the overflow time. If they want the concentration at 200, just when it overflows, well, it's going to be 1/2 minus 200 to power of 2/3, and this is going to be at overflow, this is the volume, is 800 to power of 5/3. Now that answer by itself is acceptable, but if you want to clean it up some, you can do a little bit of simplification. That's entirely up to you. So this is 200 to power of 2/3. Denominator, I write it as 800 times 800 to power of 2/3. So I separate power 1 and power 2/3 because now I can simplify these two. So 1/2, 200 over 800, there's a quarter, over 800. You can still simplify this thing. This now becomes an issue of your algebra 1. How would you simplify that? Let me just make some side remarks, not a crucial aspect of this problem, but just to remind you stuff that you did in power 7th grade or 8th grade is going to come with us. So power 2/3 means square and then take a cube root. So square of that becomes 1/16. Now I have to take the cube root of that. Well, how do you take cube root of that? I write this as 8 times 2 just to simplify. Now cube root of 8 comes out, so that's just 1/2, and then cube root of 2 is is what is left. So concentration at 200, final answer is 1/2 minus, we wrote that as now 1/2 cube root of 2 divided by 800. So it became 1/2 minus 1600 cube root of 2. Your homework system will be happy with this. They are smart enough to know that that is same as this, but this is just for your own benefit, that you can push to clean this up quite a bit to make it more understandable as to what it is. So this is a little bit complicated. This is a simpler form of that. Okay, so that is the answer to part B. So part B was concentration at overflow time. What was the question part C? Find the concentration of salt if tank had infinite capacity, meaning infinite capacity means these walls were infinitely tall. Essentially, like this was a lake or an ocean or something. So you could just keep pouring and essentially you don't fill it up. There is no overflow time. Overflow time is very large. Again, let me see. What do you think we should do to find this? The concentration if the tank had infinite capacity. Think about it. Two approaches. One is mathematical and the other one is just direct intuition. So first is mathematical. I want to figure out what will happen if tank had infinite capacity. What should we do? Pause for a few seconds, maybe a couple of minutes, and see if you can get the answer by yourself. Okay, if this has infinite capacity, when you want to set it equal to that capacity, our capacity was 800. If the capacity is infinite, then overflow time is also going to be infinite. So t goes to infinity. So if t goes to infinity, so tank has infinite capacity, As a result, overflow time is also pushed far out. That is also infinite. So instead of asking for 200, we are just putting infinity in this. Okay, this is my concentration. If my overflow time is infinity, what happens to this fraction? Okay, pause for a second and tell me, what is this if t goes to infinity? Okay, so that's a simple limit problem. If t goes to infinity, this fraction becomes 0, and all that is left is just 1/2. So how do you write that mathematically? This is something you learn in Calculus 1. Limit of c of t as t goes to infinity is 1/2. The part D of the problem says you can justify this answer without any of the previous steps. In fact, you don't even need to take this course to come up with that answer. So that's one amazing part, that we can do a detour of this rather lengthy discussion to say at least this answer, this part of it could have been obtained without any mathematical work. Let me see if you can come by that answer yourself. Again, think about it, maybe a few minutes. How do I know that if the tank has infinite capacity, the limiting concentration would be 1/2? Does this number remind you of anything? That 1/2? Sorry. That's this number, 1/2. Why should we expect that the limiting concentration be the concentration of the incoming liquid? Well, very easy. The initial salt in the tank after infinite length of time is going to be insignificant. Whatever salt was in the tank is going to be all washed out at that stage. It's going to be replaced by that. Imagine you have a big pool. You have some salt at the beginning here, and then you have a huge amount of incoming liquid. So if you do that for a very long time, all the initial amount of salt, that is by that moment, it's all washed out, and it's all replaced by the incoming concentration. So limiting concentration meaning concentration at the limit of t going to infinity is equal to incoming concentration. So think about it and try to convince yourself. Okay, so that was an example of using differential equation to solve a very basic problem, not any more sophisticated, and something that happens in a washing machine almost. We saw that this connects to a first order ODE, that we could solve it by integrating factor. Some of the simpler versions of this same problem, you can do it by method of separation as well. Okay, I leave those problems for you to solve. And then in future lectures, we are going to take a look at some of the other examples of this thing. And until then, good luck and God bless.